Imagine you're an engineer at Google. You've just run a job that produced billions of records, new signals extracted from web pages. You want to explore them. You type a query. And then you wait. Minutes. Sometimes hours. By the time the answer comes back, you've lost your train of thought. This is life before Dremel. This is the problem Dremel was built to solve. At web scale, data lives in trillions of rows spread across thousands of machines. Traditional tools like MapReduce process this data in batch jobs reliable but slow. Scheduling, launching, coordinating 500,000 tasks takes minutes at minimum. For interactive analysis, that's a deal breaker. Dremel's goal: answer aggregation queries over trillion row tables in seconds, not hours. To understand how Dremel pulls this off, we need two ideas. The first is about how data is stored. The second is about how queries are executed. Let's start with storage. Google's data isn't flat like a spreadsheet. It's nested. A single web document record might contain a list of names, each name containing a list of languages, each language having a code and a country. This structure, records inside records inside records, is everywhere at Google. Now here's the tension. If you store each record as one contiguous blob, the traditional row-oriented way, then answering a question like, "What's the average value of one field?" forces you to read every field of every record. Terabytes of data you don't need. But columnar storage, where all values of one field are stored together, was designed for flat tables. Nobody had extended it to nested data. That's Dremel's first contribution. The core challenge: when you flatten a nested record into columns, you lose the shape. Was this value the second language of the first name, or the first language of the second name? Dremel solves this with two small numbers attached to every value, a repetition level and a definition level. The repetition level tells you where in the nesting hierarchy this value repeats. Did we start a new record, a new name, or just a new language? The definition level tells you how deep the value is actually defined. For a column with maximum depth 2, a definition level of 2 means the value exists, and anything less means a null at some ancestor. Together, these two tiny integers preserve the full record shape losslessly, while letting you read just one column when that's all your query needs. To reassemble records from columns, say, for a downstream tool that expects rows, Dremel builds a finite state machine. Each state is a field reader. Each transition is labeled with a repetition level. As values stream in, the machine walks itself through the record structure, emitting the original nested shape. If you only asked for 2 fields, the machine is smaller and faster. You pay only for what you read. That's the storage half. Now the execution half. How do you run a query across thousands of machines and get an answer in seconds? Dremel borrows an idea from web search engines, the serving tree. At the top is a root server that receives your query. It rewrites the query and pushes it down to intermediate servers, which push it down again to leaf servers. The leaves scan the actual data on disk. Then results flow back up, being aggregated at every level. By the time the answer reaches the root, most of the work has already been combined. Think about a query like, sum the item amounts, grouped by country. The root doesn't compute that sum. It asks each subtree to compute a partial sum for its share of the data. Each subtree asks its children. The leaves scan their tablets and return small per-country totals. Every level up, those totals are merged. The root only sees a handful of numbers, one per country, and adds them up. The depth of the tree matters. On a query returning about 1 million distinct groups, going from a 2-level tree to a 4-level tree cut execution time roughly in half. The root can't aggregate 1,000,000 rows from roughly 3,000 machines sequentially. That becomes the bottleneck. Extra levels spread that aggregation work in parallel. For queries returning only a few hundred groups, extra levels don't help much. The architecture matches the workload. There's another problem that comes with 1,000 machines, stragglers. At any moment, some worker is slow, a bad disk, a busy neighbor on a shared machine, a preemption by the cluster scheduler. If you wait for every last worker, your query takes as long as your slowest machine. Dremel handles this in 2 ways. It reschedules slow tablets onto other machines when a histogram of processing times shows one lagging behind. And it lets you say, I'm okay with 98% of the data. In practice, dropping from 100% to 98% can turn a multi-minute query into one that finishes in under a minute. Getting the last few percent within tight time bounds is genuinely hard at this scale. How much does all of this actually help? Consider one experiment. Count the average number of terms in a text field across 85 billion records. MapReduce on row-oriented storage, hours. MapReduce switched to Columnar storage, minutes. Dremel on Columnar storage, seconds. 2 orders of magnitude, one from the storage format, one from the execution model. And notice, MapReduce itself gets faster with Columnar storage. Column stores aren't just for databases. Pause on that for a moment. A typical dataset at Google might have hundreds of fields per record. A typical query touches a handful. Columnar storage means the disk reads only the fields you asked for. Compression works better because each column has similar values packed together. And record assembly, the expensive step of rebuilding nested objects, can be skipped entirely if your query just needs aggregates. Everything compounds. Does it scale? The authors ran a top 20 query on a trillion-row table and varied the cluster size from 1,000 to 4,000 nodes. Total CPU work stayed roughly constant, but wall clock time showed a near-linear decrease as more nodes were added. A bigger system does the same work in less time. Economies of scale actually work here, which is not always true in distributed systems. In a typical monthly workload, most Dremel queries complete in under 10 seconds. Some achieve scan throughputs near 100 billion records per second. Thousands of engineers use it for everything from crash reporting to spam analysis to debugging map tiles. It's the foundation of what later became Google BigQuery.